Hello, and welcome to Lab 5, Choose Your Own Adventure. Introduction. The purpose of this lab was to determine the effect gravity and drag force had on a falling Slinky. This was observed using visual analysis via tracker and computed using a computational model through GlowScript code. The physics principles used in this lab were Newton's second law, or the momentum principle, which states that force is equal to the change momentum per change in time, or F equals ma, and Newton's third law, which states that for every action there is an equal and opposite reaction, or more simply put, there are opposing opposite forces. For the equations, we have the force of gravity, Fg equals mg, force of drag, F drag equals negative b, v squared, v hat, Newton's second law, F equals ma, the velocity update formula, and the position update formula. Here is a preview of my results. Models. First, there was the video analysis, where the video of the Slinky was analyzed and then placed into tracker where its position as it fell was plotted, and these data points were compared with the data from the computational model. The computational model, again, is just a program in GlowScript code, and it had two separate models, a model of the Slinky falling with and without drag force. For the experiment, the recording is just a video of an extended Slinky being dropped from a stretched position. Once it was uploaded to tracker, the distance that it fell was calibrated to be about 1 meter. The initial conditions are these, and the computational model is just a model in GlowScript code to show the change position with and without the drag force. Here's the code for the gravitational model. This is the model without drag force. Here's the code for the drag force model. And here we have B, which was simply calculated through trial and error. Here are the results, and as you can see, the drag force model is much more accurate to the tracker model as the gravity model steeply declines, while the yellow and blue dots pair quite quickly, even meeting up at one point. So for the discussion, why does the bottom of the Slinky stay motionless? So if you did watch this video that was posted as one of the videos we could discuss for this Choose Your Own Adventure lab, you can see that when they drop the extended Slinky, the bottom of the Slinky stays motionless until about the top of the Slinky hits it, and then they fall in unison. So why is this? While stretched, the Slinky acts as a massive spring, with the bottom of the Slinky being affected by the opposing forces of both gravity weighing down on it and the tension from the top of the spring. So when the top of the Slinky is released from rest, it begins to fall. However, the bottom of the Slinky doesn't know yet that it's falling until the information is sent down in a wave through the Slinky. So once the information is finally registered by the bottom of the Slinky, the top of the Slinky has already reached it, making the Slinky travel in unison as a connected object. In conclusion, this experiment showcased how gravity can affect objects in various ways, and depending on how force is felt by the object, there may be differences in how the object experiences and registers the force, taking longer or shorter depending on how close that part of the object is to the initial contact of the force. Thank you for watching.